From red teaming AI agents in lifelike Gmail, Slack, and payment systems, to using causal machine learning and exact optimization to decide where wildfire crews can save the most acres, to tightening the theory of uncertainty in bandits and reinforcement learning, these papers reveal AI at its most practical and its most fundamental. Together, they show how modern methods are exposing hidden failures, making high-stakes decisions smarter, and pushing the mathematical limits of learning under risk. Let's explore the first paper, Decoding Trust Agent Platform, DTAP, a controllable and interactive red teaming platform for AI agents. DTAP introduces the first controllable, interactive red teaming platform for AI agents by coupling 50-plus faithful simulations of real services such as Gmail, PayPal, Slack, Salesforce, CRM, Windows, macOS, and airline booking systems, with 14 domains of policy-grounded risk taxonomies. Its core novelty is DTAP Red, an autonomous attacker that searches prompt, tool, skill, and environment injection vectors, and iteratively improves attacks using a verifiable judge that checks concrete environment state rather than model self-report. From 6,682 curated tasks in DTAP Bench, including 3,876 red teaming cases covering 4,000-plus malicious goals and 300-plus risk categories, the authors show that state-of-the-art agents remain highly vulnerable despite strong benign capability. Google ADK with Gemini 3 Pro reaches 55.7% attack success rate under indirect attacks in the full benchmark, while OpenClaw with DeepSeek V4 Pro reaches 59.6% under direct attacks. Even Claude Code, the most robust system, still exceeds 25.2% ASR. The paper's most important finding is that attack success is often driven by compositional injections and harness design rather than model scale. Skill and tool-level injections outperform environment injections in multiple domains. Batch tool invocation can trigger an execute then refuse failure mode, and framework changes alone can reduce ASR by about 31% with only a 2% utility loss in CRM. The result is a reproducible security evaluation stack that exposes how agents fail in realistic workflows, not just in isolated prompt refusal tests. Let's explore the second paper, Predictive and Prescriptive AI Toward Optimizing Wildfire Suppression. This paper integrates causal machine learning with exact integer optimization to allocate scarce wildfire crews across simultaneous fires. Using 8,336 fire day observations from SIT, 209 ERA 5 weather reanalysis, landfire terrain and fuel layers, and 6.4 dimensional alpha earth embeddings, the authors estimate a counterfactual fire growth model with double machine learning and light GBM, cross-fit by incident to reduce leakage. The treatment variable is IHC equivalent suppression effort, calibrated to 63 personnel per crew. The learned response curve is smooth and decreasing, unlike ordinary least squares, which incorrectly associates more crews with larger growth because of confounding from historical dispatch. They then embed this predictor inside a two-dimensional fire state network over area and momentum, and a time-space rest network for crew routing and mandatory rest, yielding a two-sided set partitioning formulation with linking constraints between fire demand and crew supply. To solve it, they introduce a two-sided branch and price and cut algorithm with three novel components: column generation for fire plans and crew routes, augmented GUB cover cuts that tighten the knapsack-like relaxation, and a dual-aware maximum variance branching rule that guarantees finite convergence. On real 1-4-day instances from 2023-2024, the method solves otherwise intractable cases to within 0.07–1.15% optimality gap and predicts roughly 332,109 acres saved versus no crews, about double the best greedy baselines. Inter-GACC pooling adds another 47,982 acres saved, a 15% improvement over intra-GACC allocation. Let's explore the third paper, Unified Framework of Distributional Regret in Multi-Armed Bandits and Reinforcement Learning. This paper introduces a unified distributional regret framework for stochastic, multi-armed bandits and episodic reinforcement learning, where regret is bounded uniformly over all confidence levels delta rather than at a single fixed delta. The central algorithm, EQO+, is a UCBVI style method with a two-term exploration bonus, min, C1, KN, C2 K square root n, which lets the analyst tune a three-way trade-off between minimax regret, tail risk, and gap-dependent behavior. The novelty is not just a sharper bound, but a sharper object. Distributional regret, defined as the quantile function of regret, directly characterizes the full tail and implies expected regret by integration without the usual extra log k penalty. In multi-armed bandits with A arms and horizon t, the paper proves an O square root at log 1, delta distributional bound, and an O square root at expected regret bound, confirming a conjecture from Lattimore and Sapesvati, Doismul Event, section 17.1, and matching minimax lower bounds up to constants. In tabular RL, the same framework yields instance-independent and gap-dependent bounds under a unified sub-exponential noise assumption that covers bounded rewards and sub-Gaussian noise, and it improves prior RL tail risk results by replacing the loose OH 6 horizon dependence reported by Kodadadian and Moharami 2025 with near minimax scaling. The analysis hinges on a new quasi-optimism argument and high-probability martingale concentration tools, including a refined Friedman-type inequality, to control underestimation across episodes and states. That's a wrap on today's AI paper highlights. Thanks for watching.